So at long last, in theory, with the unit circle, we can find a whole bunch of trig values. We can evaluate sine, cosine, tangent, and all the rest. All sorts of different angles, and by different angles, I of course mean a small handful of very particular angles. If we're trying to do it for any old angle, we might need a calculator or some sort of old school table of values. In any event, once we've done that, the next thing to do is to look at graphs of the sine and cosine function. You've probably heard of people referred to things like sine waves. So both sine and cosine are going to sort of graph like waves, meaning they sort of repeat and they go up and down and up and down and up and down, and that sort of repetition goes on forever. So that's super important. That's kind of new. We don't really have any functions that sort of do that so far, right? Different polynomials and things. Sometimes they go sort of up and down a handful of times, but eventually they either shoot sort of up or down to positive or negative infinity. Same kind of thing with those rational graphs, right? There were different asymptotes and some pretty fun behavior, but there wasn't anything that just sort of kept doing this same cycle of behavior over and over and over again. So our sort of big new thing is sine is cyclic. So meaning the values repeat every 360 degrees, right, slash every sort of like 2 pi. I should kind of make a special note, I guess, as we're getting started. We're going to be using radians here. We're not going to be using degrees as our input, so we're trying to sort of make a graph, first and foremost, of just like y equals sine of x. So x here, right? So x is our theta, and theta is in radians. So the idea, right, is the sine graph, if we think of ourselves sort of moving around the unit circle, all those different values that sine takes on, right, it's sort of taking on the y coordinates as we sort of go around the circle. So at the very least, once we sort of get all the way around, right, we're sort of starting at right, like 1, 0, up and around. Right, we've got sort of 0, 1, negative 1, 0. This is going to be 0, negative 1, and then back all the way around. So as our angle cycles through all those values, our sine function sort of takes on the y coordinates. So it sort of goes from 0 to 1 to 0 to negative 1 back to 0, and then it repeats, right? So sine is cyclic, so it repeats every 2 pi. This is sort of one of our like key pieces of information. We can make a little like table of values, and what we'll do is we'll base it on 5 key points, and those are essentially going to be our quadrant angles. So we'll sort of base it on 0, pi over 2, pi, 3 pi over 2, and 2 pi. So if we go, right, kind of x, y, what's going to happen here, right? So this is sort of our theta. The y value, right, is the sine at theta. So when the x value is 0, our y value is 0. Just pulling these right from the unit circle. When the angle is 90 degrees, right, pi over 2, the y value is 1. When we're at 180, we're sort of going up, right, and then back down to 0. So that's going to be pi in radians. So that's back down to 0. When we're sort of straight down, 3 pi over 2, the y value is negative 1. And if we go all the way sort of back around to 2 pi, back where we started, we're going to be back at 0. This kind of breaks our function into stages, really. We sort of have these like middle values, kind of middle, where we hit these zeros, and then we have a max value of +1, right, where we're sort of peaking on the circle, and we have a minimum value at -1 that sort of corresponds to this 3 pi over 2, this like 270. This whole cycle, so from 0 to 2 pi, so one cycle is going to be called the period. So these are often referred to as, cyclic or periodic functions, right? So having a period, right, is sort of an amount of time that we're sort of cycling through. And so the length is going to be 2 pi, right? So this is essentially one full rotation. Now, when we graph this, right, we're not trying to sort of graph it as a circle. We're trying to sort of graph x and y coordinates, where the x coordinate is your angle and the y coordinate is your sort of output value, right? So we're trying to graph y equals sine x. So that means like an xy point is really like an angle and then the sine value of that angle. So it's interesting, if we think of this in terms of the unit circle, where we also have x's and y's, we're changing the role here a little bit. So the angle that we're sort of rotating through is actually going to be the x value, and the y values are going to sync up with the y values on the circle. So it's not just going to be sort of two circles cycling around. It's a little bit different. It makes this wave, right? This sort of curve that goes up and down and up and down. Let's plot this stuff. So it's not too tall, right? So what we're going to do, we've got these 5 key points. So maybe halfway is here. Maybe our halfway value here is pi. Maybe 2 pi is here. We have sort of a quarter point and a 3/4 point. Obviously 0 is here. This would be, right, pi over 2. And this guy would be 3 pi over 2. I'm not necessarily going to do this to scale, right? So we're doing our x values in terms of pi, in terms of the radians. So like 2 pi would be, 6 1/4-ish. Right? Pi over 2 is kind of like 1.5. So, 1 would be here. I'm not necessarily going to keep that same scale on my y-axis. I'm not going to do the y in terms of radians. The y values sort of shift between, right, 0 and 1 and 0 and -1. So if I start to sort of graph this, just like based on my table, so obviously I start at 0, 0. I've got pi over 2, I'm up here at my max. Right? When x is pi, I'm back here at the middle of 0. When x is 3 pi over 2, I'm down here at my minimum. And then 2 pi, I'm back to the beginning of the cycle. So what I want to do is draw a nice smooth curve, as smooth as I can, to connect all these points. I don't want to try to draw it to sharp corners or anything. It sort of roughly goes like this. And then what you can do is you can imagine that, this cycle, the whole idea here is that this is going to continue and keep going with the same behavior in both directions. So if you want, you can kind of put a couple more tick marks here. I'm not going to necessarily kind of mark them specifically, but you can imagine our curve would continue in the same kind of pattern, right? Doing something kind of like this. So it starts in a middle, a maximum, a middle, a minimum, and then back to the middle. Couple properties, right? Couple things to notice. So we're sort of basing this off of these 5 key points, which are these quadrant angles. The cycle itself here is 2 pi, so I really only need to do, right, 5 key points syncs up with the length of the cycle. Just a couple generic properties. My domain here is just going to be all real numbers, right? Right? That is, right, x, which is my angle, is anything. There's no restrictions on the sine values, right? I can cycle through, positive angles, negative angles, all sorts of angles that I want. There's not going to be any issues, so these patterns will just sort of keep repeating. So our domain here is all real numbers. We're just going sort of out infinitely wide. The range is a little bit of a different story. My kind of maximum and minimum values here as far as the range go, we're really cycling between -1 and +1. We hit both of those max-min points. We had said originally when we were talking about sine values, it's supposed to be right the opposite side over the hypotenuse. And so in a right triangle, the opposite is always smaller than the hypotenuse. Kind of by definition, the hypotenuse is the long side in our right triangles. So you might say to me, doesn't that mean we should be kind of strictly between -1 and 1? And I would say, well, that's in some sense that's true if we just stick to when we can draw triangles. But at the quadrant angles, right, when the sort of sides collapse, you can't see, right? At the quadrant angles, where the sides collapse, we do hit positive, -1, and 0 for that matter. So we are going to hit those values in our range. So this is going to be our sort of standard generic sine curve. This is y equals sine of x. And so when somebody says, oh, it looks like a sine curve, this is what they mean, this kind of behavior, right? If you were doing applied kind of stuff, you can use these sine curves to model any kind of repeating behavior. So obviously something like waves on a beach, right? Where you think of sort of waves coming in, but even something sort of more general like the tides, right? Cycles of the moon, anything that has to do, right, with things that repeat. So tides and cycles of the moon are connected, related to the moon rotating around the earth. Seasonal temperatures, right? But even something like alternating current, right? Alternating is sort of there in the name of it. I don't know exactly how that works, but there sort of is a positive and a negative charge, and it's alternating back and forth. So you have this kind of wave behavior. Something like sound waves have these same kind of properties. If you've ever seen a wave form from a song, you can sort of see the wave form, right, going up and down. So all this stuff is related back to sine curves, and we need this sort of sine curve model to be able to work with these things. What we're going to do next is start to transform it. So this is the generic version. If we want to actually sort of do anything with this or have it sort of sync up to a specific scenario, we're going to have to know how to change this and modify it. So that's going to be next.